Hi class, we are on to chapter 3.3, a very important section. This is inverses. So we're going to be talking about the inverses of a matrix, how to find the inverse, properties of the inverse, and uses of the inverse of a matrix. So let's start off with a theorem. Okay, so we'll have a theorem and then a rigorous definition, and then we'll start to play with our things, right? So if we have a linear transformation, right? So remember 3.1 was linear transformations. If our transformation is from Rm into Rn, so I have m variables and n equations. If this transformation is onto and one-to-one, so that means that the columns are linearly independent and that it spans my range, right? Then the transformation is invertible. Okay, so T inverse, or the inverse of T, from N to M, right? So I'm going backwards. I'm going from my range to my domain. So the inverse of T, which goes from Rn to Rm, will be defined as the inverse of T of a vector y. So I'm taking an output and plugging it in, and it will bring me back to the input that I started with. Okay, so if this is the inverse, then this is the standard linear transformation, right? I plug in x, I get out y. Then for the inverse of that transformation, I plug in y and I get out x instead. Okay, and if T is invertible, that means that m and n have to be equal, meaning that we will have a square transformation matrix, right? And T inverse is also an invertible linear transformation. So if T is invertible, then I'm going from N to N or M to M, okay? And I can also invert my inverse. So I should be able to go into my space and go back and then go back again, right? So an invertible linear transformation T and its inverse, T inverse, satisfy the following equations. Okay, the transformation of the inverse transform will bring you to just x. Okay, your starting point. And the inverse of your transform will also bring you to just x. Okay, therefore, if a transformation matrix, if a linear transform is given by a transformation matrix times a vector, which it always is, right, equaling y, then T inverse of y is really just the same thing as plugging in T inverse into A of x, and my inverse function, my linear inverse, my transformation inverse, is really just going to have a matrix that is the inverse of my transformation matrix. So a matrix times its inverse will give you out just x. So this is a small, real quick, proofy type of definition here. Okay, so let's bring it back to another theorem. If I have an n by n real matrix that I call A, and it is invertible, so this symbol right here means that there exists. The exclamation mark means a unique. Okay, so if my matrix has real entries and is a square n by n matrix, it is invertible if there exists a unique matrix B that has entries that are real numbers and B is n by n, such that if I multiply A times B together, I will get out the n by n identity matrix. Okay, so let's go through this one more time. A is a real square matrix, and it is invertible if there is a unique square matrix with real entries, such that if you multiply A and B together, you will get out the identity matrix that is also n by n. Okay, note that if I were to swap these as well, I would also get the n by n identity matrix. Okay, so B is what we call A inverse, right? So we were calling it a different name, but the standard notation for this special matrix that when you multiply it times A on either the right hand or the left hand side and get the identity out is called A inverse, the identity matrix. Okay. So let's do an example. So we're not going to find the inverse, but we are going to just give it to you, right? So let's say that A is 1, 2, 0, 1, and I have a matrix B that I call 1, negative 2, 0, 1. Okay. Now if I multiply these things together, I'm going to get 1, 0, 0, 1, right? This is 2 by 2, this is 2 by 2. I have the 2 by 2 identity matrix. So we can double check this real quick. 1 times 2 times this. 1 times 1 is 1, 2 times 0 is 0. So 1 plus 0 is 1, right? This row times this column will give me a negative 2 plus a 2 is 0. This row times this column, 0 and 0 is 0. And then this row times this column is a 0 plus 1 is 1. Okay, so you can do that as a quick check for yourself, even though we just did it. And if I swap the order around and I multiply this one times this one, I should also get the identity matrix. You can go ahead and check this one as well, right? So this one in front of this one. So this row times this column, this row times this column, this row times that column, and this row times that column, and you should see that you come out with the identity matrix as well. And since that is true, that means that B is the inverse of our matrix A. We could also say that A is the inverse of B. Okay. And A inverse times A is going to give me out the identity matrix, which it does. Okay. So that's B times A here is the same as A inverse A because I'm calling B my inverse. And I also have A times A inverse, A times its inverse, equaling the identity matrix as well. Okay, so again, notice I did not put the subscript of I2 here. As I said before, for the identity and the zero matrices, we don't generally write the subscript. However, in my definition, I decided to put it so that we understand that this is the identity and then it's squared with the dimension of n, since we're have two n by n matrices that we're multiplying together, right? So that was to drive in the point for the size of the output that you should be getting. However, as I said, we don't really care about the dimensions of I. It should make sense when you do your math, right? I'm multiplying two 2 by 2 matrices. I'm going to get out a 2 by 2 matrix, right? So an invertible matrix is called non-singular. Now this is generally confusing because you would think an invertible matrix would be called singular because it's unique, etc., etc. It is not talking about the number of matrices here. It is just it's an antiquated term. When you take differential equations, you'll see non-singular terms as well. They're very, they're a common reference to, it's basically things that work or not, right? So, if a matrix is not invertible, it's singular. Okay, so singular means you cannot, it is not invertible. Non-singular means it is invertible. I will go back and forth in my notation and verbiage as we go through these videos and calling it non-singular and invertible just so that you get used to relating those two terms together. Okay, so I want to make a big point of it now so that you don't get confused later when I say, oh, this thing is non-singular, and you're like, wait, I thought that meant you can't invert it because not invertible, right? No, nope, it's opposite. Invertible is non-singular. Okay, not invertible is singular. So you're kind of switching around the no terms from invertible and singular, not invertible and singular, right? So those things are kind of swapping. Okay, so just remember that. Just remember one, invertible is non-singular. Okay, invertible is non-singular. And then it's easy to remember the other half of that. Okay, so let's do a theorem. Let's say we have two matrices that have R entries each. Both of these matrices are n by n. And then let's take another two matrices and have those matrices be n by m. Okay, then A inverse is invertible, and the inverse of the inverse will bring you back to the A matrix. Okay, so you can invert an invertible matrix an infinite number of times, basically. Okay. A times B is invertible, and AB inverse is going to be B inverse A inverse. Right? So this is important. So remember what we talked about for the transpose. If I have two matrices being multiplied together and I take the transpose of that, it was the same thing as me reversing the order and taking the transpose of each. It's the same thing for inverse. I reverse the order, okay, and I take the inverse of each. We call this the socks and shoes method. I'll explain that a little bit later when we use this in practice. But basically it's saying you got to take off your shoes before you can take off your socks. So the order gets reversed when you're doing your inverse. Okay, we'll talk about that later. If A times C equals A times D, so again, notice that the dimensions are going to match here, right? I have an n by n times an n by m, and an n by n times an n by m as well. If your matrix is square, in this case, okay, then we can say that C equals D. So remember before we said that this was not always true. It is true if it's a square matrix on the edge, okay, on the right hand side or left hand side. If A times C equals 0, then C is going to be the 0 vector. So again, remember we talked about this before when in the last section actually, when we talked about properties of matrices. We said this does not necessarily mean that C would equal 0 in this case. It does if you have an n by n matrix as one of your factor matrices, one of these matrices you're using to multiply by. Okay, so it's only when you have a square matrix here that these two properties work. If A was not a square, then these would not hold true. Okay, we talked about in the last video. Maybe you want to go back to the write-up and look through that, or maybe you want to go to that last video and just review that small portion of it. Okay, in 3.2. Big mark here. There is no such thing as division of matrices. Okay, do not ever and you'll see how we actually do it. But no, if you ever say, hey, this is A divided by B, I'm instantly giving you 0 points. Okay, you cannot divide a matrix by another matrix. Never. There's no such thing. We do not have a calculation for that. Okay. However, we have an equivalent method of division by using inverses of a matrix. Okay, so I'll go through an example of that right now for you so you can see how that works. Okay, but never ever divide one matrix by another. There's no operation for that. It does not exist. So when we do try to solve a matrix equation, we have to think of our left side multiplication and our right side multiplication as two completely different things. Now, I've said this a couple times in previous videos, or I guess in the last video. So we're really going to drive that point home today. So remember, AB does not necessarily imply that BA is the same thing. Okay, so AB does not mean that BA is equal to AB. Right? So left side multiplication and right side multiplication give us two different matrices for the most part. Right? So I'm going to give you an example. We're going to kind of throw it way back to something you guys are more familiar with, which is standard algebra. Right? I know I've been yelling at you guys saying, don't do regular algebra, linear algebra. So let's go back to standard algebra, algebraic methods, just to see how they are similar for solving matrix equations. Okay, because we will have matrix equations that we'll need to solve, right? So let's say back in the algebra days, I had this equation, okay, and I was asking you to solve for x. So right now, this is not vectors, these are just regular variables. First things first, right? Take my equation. So all I did really was rewrite my equation. If I'm trying to solve for x, we know that we want to get all of my x's on the same side. So we can do that a couple of different ways, right? So what I'm going to do first, however, is I'm going to multiply these two things together, right? And then I can subtract my 10x on both sides, right? Then now in order to get x alone, I would have to factor this out, okay? Because remember, I'm solving for x, not a constant in x, so I only need to factor the x. I don't need the GCF here. I don't need to factor 2x, just the x. So now if I want to finish getting x alone, I would divide both sides by this term. Okay? Very standard. That's what you're used to. So that's what we want to move away from. We want to stop thinking about it as division. Okay? I actually tell this to my algebra classes all the time, that we're not actually doing division. We're doing a multiplication, right? Division is just multiplication. So you need to think about it in terms of multiplication instead of division, right? So again, to think this another way, we could apply this step in a more algebraically rigorous manner, okay? Because in an actual study of algebra, we don't have division, okay? Division is just an algorithm that we apply for separating numbers into equal pieces. In the study of algebra, however, we think about multiplying by inverses, right? 8 divided by 2 is the same thing as 8 times 1/2, right? So we want to think about multiplying things by reciprocals, by their inverse values, okay? So let's say that we just take the last step. So these dots mean I worked all of these 3 previous steps here, and I got to this result, okay? So I did everything the same, and I got here. So instead of dividing both sides by 4y minus 10, I'm going to multiply both sides by the inverse of 4y minus 10. And when I say inverse, I don't mean the inverse as in a function inverse. I mean the reciprocal, okay? So to the power of -1. So I'm going to multiply this side, right, times 4y minus 10 to the -1 power. And I'm going to do the same thing to y, right? And so we know how powers work. I have the same base. I have 1 plus -1 gives me a power of 0. Anything to the 0 power is just 1. These things cancel out, or you can think of it as 4y minus 10 times 1 over 4y minus 10, right? They cancel out. And I have the exact same answer, but now it is in a power form, right? Rather than looking like a rational function, okay? So obviously if this was algebra, I would tell you this is the way I want your answer, because that's an algebraically efficient way of writing a solution. However, the way that I want you to start thinking about it is in this way, because this is how we're going to solve our matrices, okay? So this is in line with how we think of solving matrix equations. So what we're going to do is we're going to come back to our equation here, and we're just going to make a quick substitution, and we're going to solve it in this manner, right? So if I'm solving a matrix equation, so instead of x and y being variables, they should be matrices, okay? So let's say A and B are n by n matrices, so that the dimensions match up as we do our calculations, okay? Then this is going to change to this. Instead of 2x, I have 2a. Instead of 2y, 2b. Instead of 10x, 10a. And instead of plus y, plus b, okay? Pretty much everything gets to be done the exact same way, because these dimensions match. This is really a times b times 4, right? Because I can pull out the scalars and multiply the scalars together, and I can multiply the matrices together. Not only that, but the matrices are both square, so the dimensions match up. Here they're both square, so they can be added together as well. The dimensions match everywhere, right? So I'm going to have 4ab equals 10a plus b. Same thing as before. I can subtract my 10a to both sides, okay, just like before. And I can still factor out a common multiple, okay? So if I pull out the 10, pull out the a, think about this as 10 times a times I, right? So when I pull it out, I'll be left with an identity matrix here, okay? A times 4b minus, I know I have it as just 10, but there is an identity here. We tend to just not write the identity matrix everywhere, right? It's kind of implied that it's here, okay? So don't freak out about that. And then as you can see, I have just that B that was left over on the other side. So now if I want to get rid of this, I multiply it by its equivalent matrix. And in order to get rid of it, I have to multiply it on the right side by its inverse. Okay. Now when I multiply by B, I also have to multiply it on the right side, because if I don't have the same thing, right? I can't multiply this on the right side and this on the left side. They both have to be on the right side of the equation. Because remember, right-hand multiplication and left-hand multiplication are equivalent, okay? Or they're different things. So when I do this, I'll be left with A because I have a matrix times its inverse, which will leave me times A times the inverse, which is just A, equals B times 4B minus 10, okay? Inverse. I cannot write this as a reciprocal function. I cannot put B over this thing, because then that would imply that I'm able to divide B by another matrix. This is a matrix times another matrix. There's no division going on here, okay? So do not write reciprocal functions, expressions, anything like that. This is it. This is my answer, okay? So note that on the right-hand side, B cannot distribute across the parentheses. I cannot bring this across because I have this inverse power here, okay? This cannot be 4b squared minus 10b. I cannot distribute b. This is the final answer, okay? Also note that if maybe I had done the left-hand side instead of the right-hand side, I would have had something completely different, okay? So if I worked my way down to here, and then I decided to multiply by the inverse on the right side on the left side for some reason, that would not have given me anything. This and this would not have canceled out at all because I have the A matrix in the middle. There's no way for me to get this thing over here on the right side. I can't just throw it in the middle of something, okay? I would have came to a dead end and this would have been it, right? So you can't multiply this on the right side and then think that it disappears over here because you multiplied it on the right, right? If you multiply it on the right, you got to multiply it on the right on both halves of the equal sign. You can't do one left and one right, okay? And so our result here is not A, it is this inverse matrix times A times this matrix. If you had actual values for A and B, you would easily see that this is not the same as whatever your A matrix would be that you choose it to be, okay? So very, very, very important. Those are the slight differences you have when you're doing solving matrix equations. So let's go back to the last theorem. So we just did a small exploration. We're going to use this idea of solving matrix equations to prove B from our previous theorem. Okay. So a typical thing that we do in a class is we are presented a theorem and then we prove things of that theorem, right? So this is a 4-prong theorem. We're going to choose B. We're going to solve this, okay? So just a heads up, on your exam, whenever that is, any one of these theorems, I may choose and then say, hey, I want you to prove, for this theorem, prove part A, right? Or go to a theorem from way, way, way in the beginning and say, prove this theorem. Or, you know what I mean? I can say, prove all 4 of these items from this theorem, if I were to present this, for example, right? So that's a common thing in a course like this, where proofs are involved. It's for you to prove these theorems on your own. So let's see here. What do we got? Okay, so we're going to prove that theorem. So just to come back, AB is square. If A times B is invertible, then the inverse is of that product is going to be B inverse times A inverse. Okay, so that's our proof. So I need to have 2 invertible matrices. Okay, in order for them to be invertible, they have to be n by n. So they have to be the same dimension and invertible. So that's the first setup. Okay. If this is true, if A and B are both invertible and they both have the same dimension, then that means I can multiply them together and have an actual matrix out, right? Now, if these had different dimensions, I wouldn't even be able to multiply this out. So I basically said both of these are invertible and their dimensions match up. And since they're invertible and the dimensions match up, they're both the same. They're both n by n, basically, right? I'm going to define, or not define anything. So if I take this, okay, and I multiply it by A inverse on the on the left side, okay, then I'll have A inverse times AB equals B, right? So if I multiply this by A inverse on the right side, A inverse times A goes away, and I'm left with B. So I have this equation. A inverse times A times B will give me B, okay? And if I'm left with B, if I go B inverse times B, by definition, I also will get the identity matrix out, okay? Therefore, if I take AB and multiply by A inverse and times B inverse, I will have B inverse A inverse times AB. Okay, so now what I'm doing is I'm just grouping these two together and these two together. Okay, and that is going to equal I, right? Because if we think about this, I showed that if I multiply A inverse times A, I get B, right? So I basically said, what happens if I multiply this first? I get I, so I get B inverse I, B. And so that leaves me with B inverse B, which gives me out I. So I'm pulling this apart into sections, right? I showed one piece at a time. And so this whole thing, I can then separate into two halves because that's what I'm trying to prove, right? The thing that I'm trying to prove is that AB inverse is the same as B inverse A inverse. I'm trying to show that one is the inverse of the other, okay? Which is I, right? And so if these two things equal I, then what can I do? I can take this equation. So I'm thinking about this is one equation and this is one equation now. So let's say I take this equation and I multiply it on the right side by AB inverse. That means I have to multiply this on the right side by AB inverse, and I'm left with B inverse A inverse equals AB inverse, which is what I have here. Okay, and that's my proof. So there's just a little bit of tricky manipulations going on, but we got to the end result. Okay, now that's the end of the proof. Okay, so now let's talk about finding an inverse matrix. We've talked about the properties, we've talked about how to use them to solve matrix equations, but we have not talked about how to actually find an inverse yet. And actually this is a very, very large discussion. We're going to talk about one way right now, and then we'll talk about two other ways in chapter 5, okay, which is the next chapter we're going to go into. We're going to skip 4, come back around for it. But let's go ahead and look at finding an inverse, okay? So there's an algorithm for this, okay? Now the algorithm is to take your matrix that you want to find the inverse for, and then you partition it, and on the right side you throw in the same size matrix but the identity. So you're gonna have, so let's say you have a 3 by 3 matrix, you're gonna create a 3 by 6 matrix, where half of that matrix is A and the other half is the identity matrix. Okay, so you're creating sort of two halves of a single matrix, right? And now what I want to do is I want to take my A matrix and I want to reduce it down with my row operations using Gauss-Jordan, and I want to create A into the identity matrix. Okay, so my goal is to turn A into the identity matrix by using my row operations. And as I do that, I is going to transform into the inverse of A, right? So I'm going to find my inverse matrix by creating a partition and using Gauss-Jordan elimination, where one side is going to transform from A into I, and the other side is going to transform from I into A inverse, okay? If I cannot reduce to I, okay, so I have a dependent system, free variables, a false equality, right? Any of those kind of weird things that pop up, okay, then that means that my matrix is singular. Okay, so remember what singular means? So my matrix is singular. That means that it is not invertible. Okay, it is not invertible if I cannot reduce my A down to I. Alright, so let's go ahead and do an example. So let's take this 3 by 3 matrix and find its inverse. Okay, so 1, negative 1, 0, 2, 1, 1, 0, 2, 1. So our setup is I put A on the left side, put the identity on the right side. Okay, remember the dimensions have to match. Okay, 3 by 3, 3 by 3, that gives us a 3 by 6. I will apply my Gauss-Jordan algorithm correctly, not in some weird ass order, right? I want you guys to do this in the correct order. So my first thing obviously here is to get the value below it to be 0. So the first movement that I'll have is going to be R2 becomes R2 plus R1. Okay, it's the most obvious thing, so I can make this 1, 0, 0 below it. And so then that will change this row completely. Okay, so the first thing that's going to happen over here is you're going to see the elementary matrix form, right? So this will be 1, 1, 1, 0, 0, 0, 1, because since it's the first movement and this is an identity, it'll just be the elementary matrix form. Okay, and that's the only time that's going to happen because it's the first one, right? So the next thing is I would like to get this to be a 1. Okay, so I can do that by dividing by 3, which is terrible. I can make this, I can say R2 becomes R2 minus 2R3, but that's terrible. Easiest thing is just to swap these rows because it's a 1 under here already. So this will be what I do. Okay, I just swap these rows out. It makes it easier. And then now I can eliminate this bottom one because remember I'm trying to get 1 zeros, 1 and then a 0 and then a 1. Okay, and then I can move into my backwards phase. So I'm going to take this. So the next move will be R3 becomes R3 minus 3R2 since this is a 1. Okay, and so then that's going to change things quite a bit as well. Okay, so now I have a negative 1 here. So then obviously I can just change all of these to a positive 1. Where I can use it first, I guess, is what I do here to make this a 0. Right, because now I'm beginning the backwards phase, so I'm going to make these things 0, which is really only this one. Okay, now I can change the sign here. Okay, get rid of this term, and then change the last one, right? So this that I have over here, once I change the signs, is my inverse matrix. Okay, so I reduce this down into the identity. Right, so change all the signs here to end up with this, right? And so we can do a check. Okay, I'm not doing a check here. I'm going to do something else real fast. But if I wanted to check, I would multiply this matrix times this matrix, and I should get the identity out. Okay, I'm actually going to show you something else. It's pretty cool. So let's do that right now. Alright, so what we're going to do is we're going to go through each of these movements that we had. Okay, so let's make a note of it. We have R2 plus R1, swap the rows, another R3 minus 3R2, R2 plus R3, R1 minus 2R2, and a negative, right? We're going to take these and we're going to form the elementary matrices. Okay. So this was the first one that I had. We're going to call it E1. And this is the elementary matrix we get from adding R2 to R1 and making that my new R2. Okay. The next move I had was swapping the rows of R3 and R2. So I'm going to form the elementary matrix by swapping those two rows. Okay. I'm not doing that to this. I'm doing that to the identity, right? To make the new elementary matrix. The next move I did was R3 became R3 minus 3R2. So I'm going to write that elementary matrix. Okay. So I'm going in order. E1, E2, E3. The first movement, the second movement, the third movement, right? If we come up here, first movement, the second movement, the third movement. The fourth one should be R2 becomes R2 plus R3. Okay. So the fourth one is R2 becomes R2 plus R3 is the fourth one. Okay. This would be the fifth. Okay. R1 minus 2R2 becomes R1. And R3 becomes negative R3 would be the third movement, right? So each of these are elementary matrices. I'm doing these operations on the identity matrix, right? So now what's going to happen, okay, is if I started off to get my A inverse, right, what I did was I took my A and I multiplied it times the first elementary row operation, right? It's first elementary matrix. Because that result, if you remember from my previous video, that result is how you get, right? Is how you go from the first move to the second move to get this result on A, right? We saw that in a previous video, okay? And then from here, I applied this movement to get here. So what I did here, so what I'm doing is that one I just looked at would be to this, I apply the next move. Okay, I did a similar expansion before, right? So basically every single time I have to write my multiplication on the left hand side because it's kind of like I'm transforming my previous matrix by multiplying it by a new matrix. So this is the order I go times my original matrix A. I multiply times E1 and then E2 and then E3 and then E4, then E5, then E6 in order to get to A inverse. Okay. If I multiplied all these matrices out, this one times this one times this one times this one times this times this times A, I will come out with my A inverse. Okay. So this is a factorization actually of A inverse. If I said I wanted to decompose A inverse into elementary matrices, right, times your original matrix, this is what that decomposition would look like. Okay. So A inverse is now written as it is a product of 7 different matrices. Okay, I decompose it into 7 matrices. So what we're going to do here is I'm going to take this, okay, I didn't move anything, I just rewrote it here. It's in the same order. And notice what happens when I start to peel these things off, right? So if I want to get back to A, I can multiply this on the left-hand side by E6 inverse, and this by E6 inverse. Okay. And then I can peel off E5 by multiplying it by E5 inverse and E5 inverse. And I can continue that pattern until I reduce my way all the way to A. And as you see, I have E1 inverse, E2 inverse, E3 inverse, etc., all the way times A inverse to equal A. So now I have a decomposition of A into elementary matrices, inverses of elementary matrices, and A inverse. Okay. These themselves are actually going to be elementary matrices as well. Okay. So if I multiply A inverse, so what I'm showing here, okay, is that A inverse, okay, is the same as these elements. Okay, if I wrote A inverse, I would have these elements. So A inverse inverse is A, right? So if I took these and I took the inverse, I'm going to get out A. A is also equal to these things, so I can equate their parts. Okay, so do you remember what we said about taking the inverse of a product of, if I have A, B inverse, then I basically reverse the order and I inverse both of them. It's the same thing here. If I have all of these things, if I want to change them around, right, and equality would be E6 inverse, instead of being at the end, being at the front. And E1 inverse, instead of being at this end, being at this end instead. And the order of all of them swap out, right? That was very similar, or it's basically an extension of the property that we proved, this. A and B both being invertible, the product being inverted, you swap the order. Okay, you would do the same thing if you had several products one matrix that was factored into several products. Okay. So the orders all switch, and they each get their inverse is the equality that we can show here. Okay. So again, a good property to understand about inverses and how they work, very similar to when you're transposing a product as well. Okay. So this is what we're calling the socks and shoes method. Okay. If I want to get to A, right, this is my foot, and I have several layers of socks and shoes on, before I can get to my foot, I gotta take off my shoe, and then I gotta take off my socks, right? So we're peeling them away, and that's why they go into the opposite order on the right side or the left side if you're trying to whittle your way down to a single matrix that you're interested in, right? So as you saw here, I had this equality, okay? And as I said, in order to get towards A, I gotta take off my shoes, okay? And then I need to take off my socks, right? And then I gotta take off my under socks. And then I gotta take off my, I don't know, if you have 6 pairs of socks, right? You have to take each thing off in order to get down to what it is you're interested in. So that's the way the inverses work, and that's why we call it socks and shoes property, because generally we don't have 6 things we're looking at. We have 2. I take off my shoes, then I take off my socks, and then I have the matrix that I want, right? This is just an extreme case, because if I show you something extreme like this, then it should ideally make more sense for how this works in general, right? So let's come down to something that's much, much easier to calculate inverse-wise, which is a 2x2 matrix, okay? For a 2x2 matrix, we have a closed form. We have a closed formula for it. It's very easy to calculate a 2x2. After a lot of practice, you should be able to look at a 2x2 and be like, boom, this is what its inverse is going to be. Okay. It really is not a lot of calculations, and you should be very, very quick at finding the inverse of a 2x2. So if this is my matrix A, B, C, D, to find the inverse, what's going to happen is this diagonal is going to swap rows or swap positions. So you'll have a D here and an A here. Okay. C and B will turn negative. So you swap these positions on the main diagonal. The secondary diagonal turns negative. Okay. And then you multiply times A times D minus B times C. Okay. As a scalar. So A inverse is AD, this diagonal product, minus this diagonal product, okay, under 1. And then A and D switch, and C and B position-wise become negative. It's very, very easy. It's very easy to get used to once you are familiar with it. For the first few times, you're probably going to have to look at this and be like, oh, okay, I have to follow the formula. Okay, but ideally, for the 2x2, you should learn this like the back of your hand. It'll make this class way, way, way easier to deal with. So let's look at an example. Okay, or I guess let's go through the steps and we'll look at an example. So multiply the main diagonal entries together. Subtract from that the product of the opposite diagonal. Okay, and it's the reciprocal of that is our scalar. We're going to swap the entries of the main diagonal. We're going to change the signs on the entries of the opposite diagonal. Okay, and then we multiply the resulting matrix by the reciprocal of the value that we found here in A. It has a special name to it, but we'll talk about that later. Okay, chapter 5. So an example for 2x2. Let A be 2, 6, diagonal 1, 4. So my general form here is going to be 4, 2, 1, negative 6. And I'm going to multiply that times 8 plus 6. So it'd be 1 over 14 times 4, 2, right? And then these will be a positive 1 and a positive 6. Boom, just like that, okay? So 1 over 8 minus a negative 6, or 14. 4 and 2 swap. Negative 1 and 6 change signs. Okay. So 1 over 14, when I multiply my scalar in, you always simplify this. Okay. Now, I said this before. keep your answers as exact values in this class, meaning simplify your fractions fully, but do not ever give me a decimal unless it's an application problem, okay? So this is going to reduce to 2, 7, negative 3, 7, 1, 4, 1, 7. And that is my inverse. Again, if I wanted to check it, I take A and A inverse and I multiply it together in any order, doesn't matter. A inverse is the identity. A inverse A is also the identity. Okay. So now let's talk about what is probably the most useful use of the inverse. There's definitely several uses of it. This is probably going to be the most useful, most beneficial for you, especially as you start to apply linear algebra to your respective fields, physics, chemistry, bio, engineering, all those kinds of things. This is the most useful use of the inverse. Now that I'm about to show you. Okay, so let's say we have a system of equations that we can model as a matrix equation, right? A times a vector equals a new vector B. So we saw this as a system of equations. We've also looked at this now as A being a transformation matrix, right? So we have different ways of representing this thing that we've seen so far in this class, right? So if A is non-singular, meaning it's invertible, okay, then we can solve for A by multiplying both sides of this equation on the left-hand side by A inverse, right? A inverse times A will give me out X, and A inverse times B will give me A inverse B. So one of the benefits of having a non-singular matrix, something that's invertible, is being able to solve these matrix equations, okay? Or your system of equations is extremely helpful. So let's consider this system. 10x minus 7x2 equals negative 5, and negative 6x1 plus 5x2 equals 1. So as of now, you have several ways of solving this. You have your traditional algebraic ways, which there's two ways there. You can do substitution, you can do elimination, right? I've told you guys not to think about that in this class, right? We're using linear algebraic methods. So far in this course, we have thought of this in terms of Gauss-Jordan elimination, okay? And so now we're throwing another method, which is the method of inverses, right? So now that's 4 different ways you have for solving any system of equations. Well, especially if it's square, okay? If it's not square, you can't use the inverse, obviously. We're actually going to develop many more methods for solving these sort of systems as well, right? So what I want to do is I want to decompose this into either an augmented matrix or a system, right? Or a matrix equation, which is going to be more beneficial to me, okay? Of course, I could have this as 10, negative 6, negative 7, 5, ... negative 5, 1. That's going to work as well, but it's better to think of this as separate things so that I can apply these matrix methods that I have. I need to find the inverse of this because this is my A, right? My X and my B. So remember what we do. These things swap. These things change sign. The scalar multiple that I have is 1 over 50 minus a positive 42. So that would be 1 over 8. Okay, so I have 1 over 8 times 5, 7, 6, 10. That's what my inverse matrix is going to look like. Okay, swap positions, change sign. This diagonal is the first number. This diagonal is subtracted from that first diagonal. Okay, so I'm going to multiply this through. I'm going to have 5 over 8, 7 over 8, 6 over 8 is going to be 3 over 4, and this will be 5 over 4. Okay, 5 eighths, 7 eighths, 3 fourths, 5 fourths. Apologies for not putting a spacer here. I'm trying to make sure to leave space next time on these matrices. So that's my inverse matrix. So remember how the solution of this looks. Okay, if this is my matrix equation, A, X, B, to solve for this, I take my inverse matrix, and on the left side of both equations, I use it to multiply times what I have, right? So A inverse times A will leave me with just my x vector. A inverse times B, if you notice the entries match up, will give me my result. Now you might be saying, oh, Professor Williams, more fractions. You guys, it's easy. It's the same denominator, okay? 5 and negative 5 is negative 25 plus 7, right, will give me 15 over 8, right? 18 over 8, sorry. Negative 25 plus 7 is 18 over 8, so that's what, 9 over 4. Then these two are going to add together, right? So 3 and negative 5 and 5 and 4. So that's really negative 15 plus 5, so I got 10 over 4. So that's 5 halves and 9 fourths. Okay, so just because of fractions doesn't mean it's going to be hard. There are already common denominators for each row here. Okay, so you're really just multiplying the numerators, and they're already common denominators. So the math is actually easy. Okay, a lot of times the math is extremely easy for solving these things out because you're always multiplying everything by the same reciprocal value, right? So you always have a common denominator there for the most part. It's not hard to do this by hand, okay? So then this is my solution to this system. And if you're like, oh, really, that's cool, I don't believe you, then that's fine. What do? You check it, right? You can take these values and plug them in and make sure they equal out. You can also take this and solve it using your Gauss-Jordan method to double check to make sure your method is correct as well, right? So there's 3 different ways for you guys to kind of make sure you're on the right path here. And that's the end of our video. Okay, I hope you enjoyed, you guys. See you on the next one.